Okay, in the last part of this lecture, we are going to look at one of the main results, a very useful result that crops up very often, and some of you might be familiar with it already. It's having to do with the bounds on the quadratic form. How large can a quadratic form be, and how small can a quadratic form be? Okay, so suppose you have a quadratic form x transpose Ax, and as usual, I'm going to assume that A is symmetric, and that A has eigenvalues lambda 1, lambda 2, so on up to lambda n, where let me assume that the eigenvalues are ordered like this, right? So lambda 1 is the smallest and lambda n is the largest. Okay, so we are going to assume that that's the order of the eigenvalues, lambda 1 to lambda n. Okay, and A is a symmetric matrix. Okay, under this context, okay, let me just state the theorem. Okay, the quadratic form x transpose Ax is always bounded between the two quantities, right? The lower bound is given by the smallest possible value of the quadratic form, which is lambda 1 x transpose x, and the largest possible value is lambda n x transpose x. Okay, now to be a bit careful when I say smallest possible value, largest possible value, I'm talking about smallest and largest provided this quantity x transpose x is fixed, right? Of course, if I increase the magnitude of x, meaning if I keep scaling x, right? If I keep scaling x with a scalar or multiply x with a scalar, this value will keep on increasing, right? Or this value will keep on increasing or decreasing, right? I mean, for example, if I multiply x with, let's say, alpha x, where alpha is a scalar, and construct the corresponding quadratic form x transpose A alpha x, you can see that this is just alpha square times x transpose Ax, right? So simply by increasing alpha to a very large number, you can actually get this value to be either close to infinity or close to minus infinity, depending on what this quantity is, right? So then there is no bound really, right? I mean, bounds only come into the picture when you can control the vector x, so that you cannot scale it uncontrolled, you cannot scale it arbitrarily, right? So here effectively what I am doing is, the one way to interpret this theorem is, let's just think of the vector x having magnitude 1, 2 norm 1, okay, meaning that x transpose x here is just 1. In that case, this simply reduces to lambda 1 less than or equal to x transpose Ax less than or equal to lambda n. Okay, that's the essence of the theorem. So what the theorem is trying to say is that if your vector x is constrained to be a unit vector, okay, then the quadratic form, the smallest possible value of the quadratic form is the smallest eigenvalue of the matrix A, and the largest possible value of the quadratic form is the largest eigenvalue of the matrix A. You can see how intricately the spectral theorem is tied with the quadratic forms, right? Even though when we started out with polynomials and degree 2 expressions, it didn't have any clear look to linear algebra, but you see that it does, right? So this is the main theorem that we are going to discuss in this portion of the lecture. The proof is actually quite straightforward because we have done most of the work, and as I said, many of you might have encountered this already. Okay, so one thing I do want to point out is that these inequalities over here are tight, right? These inequalities are tight, and generally when people say inequalities are tight, they mean that there is actually a value of x, that makes this value to be equal to lambda 1, okay, and there is a value of x that will make this quadratic form to be equal to lambda n, okay, and all other choices of x will give you a value somewhere in between lambda 1 and lambda. Okay, that's what it means to say inequality is tight, because it's very easy to write an inequality like minus infinity less than or equal to x transpose Ax. This is obviously a correct inequality, but it's a meaningless inequality, right? Because it doesn't really tell you anything, right? So tight inequalities usually are very well sought after, right? And we are trying to say that this inequality is actually tight. Okay? So to see that, it's very easy to actually guess what would happen, right? For example, if v1 is the eigenvector corresponding to lambda 1, if v1 is the eigenvector corresponding to lambda 1, in other words v1 is the first column of your Q matrix, then if I set x to v1 here, if I set x to be equal to v1, then I'll get v1 transpose a v1, right? And you can see what that is, right? Because a v1 is simply going to be equal to lambda 1 v1, and that's just going to give you lambda 1 v1 transpose v1, right? And eigenvectors, as we discussed before, typically are picked to be unit vectors, so v1 transpose v1 is 1, and we simply get lambda. Okay, so you can see that this choice of x, setting x to be equal to v1, actually makes this quadratic form to be equal to. Okay, and similarly, as you can guess, setting x to be equal to vn, the eigenvector for lambda n, will make the quadratic form equal to lambda. Okay, that's very easy to check, right? So these inequalities are tight. Okay, so let us see how to actually go about proving these inequalities, proving this theorem, right? So we have done, as I said, the groundwork. The spectral theorem, is the perfect setup for this. So x transpose ax, as we said before, is simply equal to summation of lambda I yi square, I equal to 1 to n, and recall what y is. Y is actually equal to q transpose x. Okay. Okay. So now remember that we are effectively assuming x transpose x to be 1 here. That actually means y transpose y is also equal to 1, right? Y transpose y also should be equal to 1 if x transpose x is 1. This is clear to you because, as we discussed in the first segment, orthogonal matrices don't really change the norm, right? So if x is unit vector, then applying a rotation, an orthogonal matrix will still keep it to be a unit vector, of course. So y is still going to be a unit vector. Y transpose y will be 1, or in other words, the summation of yi square, that's y1 square plus y2 square plus so on plus yn square, is going to be equal to 1. Okay, so now you have summation of lambda I yi square, right? So let us try to investigate what is the largest possible value of this expression, given that we have this condition that y1 square plus y2 square plus yn square is equal to 1. Okay, now it's very clear that summation of lambda I yi square is always going to be less than or equal to lambda n times summation of yi square. Okay, so what I'm going to do is, here you have all these coefficients for the lambda I. I'm simply going to replace each quotient with the largest one, and remember that lambda n is the largest quotient we have, right? So replacing each quotient with the largest one will only increase the value, and that's what you will get on this side, right? And similarly, replacing each coefficient with the smallest one, you will get lambda 1 times summation of yi square, I equal to 1 to n. Okay, and now you can see that this immediately gives you the inequality that you are looking for, right? This quantity here is just 1, this quantity here is just 1, so you can just get rid of it, and what you have ultimately is lambda 1 less than or equal to summation of lambda I yi square, which is actually the same as the quadratic form x transpose x. Okay, and that's less than or equal to lambda. Okay, so that's basically the statement of the theorem. Okay, so what you are trying to say here is that and this is the main takeaway from this lecture, if you are able, the main idea is that when you have a quadratic form, the largest value it can take corresponds to the largest eigenvalue, the smallest value it can take corresponds to the smallest eigenvalue of the corresponding matrix, right? And to get the largest eigenvalue, you have to set x to be equal to the corresponding eigenvector. Okay, for example, as we discussed here, if we set x to be equal to v1, then the quadratic form evaluates to lambda 1. Okay, if we set x to be vn, it evaluates to lambda. Okay, so that's essentially the gist of this result. Okay, so in the next lecture we are going to look at some applications of this, and we'll look at a generalization of slightly more sophisticated generalization of this result. Okay, if you have any doubts about this lecture, please feel free to ask me in the regular classroom slots. We'll also open up a discussion forum on Piazza, where you can post your questions and me or the TAs can get back to you with answers as soon as we can. Thank you very much.